you have that inversion, and you have you have what's called stratified atmosphere, which is technically a stratified fluid. At that point, we're dealing with fluid dynamics. So a radiation frost is a hydraulic event. It's not a weather event. The cold air will flow into areas where more cold air flow into than what will flow out of are called accumulation areas. Eventually, that cold air will begin to build up, and because air, it's a fluid, but it's also a gas. It's not a liquid. Liquids are not compressible, but gases are. So the more fluid, the more cold air that flows into a pocket, the deeper that pocket, it typically, just like fog, it doesn't get deeper that, along a straight correlation line. It compresses. So what we call the thermal gradient, which is the differential in temperature at a given height, shrinks. So instead of being at every 5 meters, for instance, of height, you typically, it doesn't lose the same amount or it doesn't gain the same amount of heat. It doesn't get consistently warmer. You may have a 1 degree temperature difference between the ground and 1 meter, but the next meter is not going to be a whole degree. It might be half a degree, and then the following meter might only be a quarter of a degree. So it spreads out. So your first 5 or 6 feet off the ground, or 2 or 3 meters off the ground, is where you have the greatest benefit. That's where that cold air mass is concentrated. Oh, and one thing, it's usually coldest before sunrise, and the reason that happens like that is for the same reason you find everything in the last place you look, because you stop looking after that. When it's right before sunrise, as soon as that's the longest time that you have, of radiation losses, is right before sunrise, and then when the sun hits the ground, that process stops immediately and reverses itself. Whoops. Okay. The cold air drain, the way that the cold air drain works, it selectively extracts the coldest air from the ground. It's basically the same thing that you do when you drain the water from your diesel tank. The water in your diesel tank might only be 1/8 of an inch, or a couple of millimeters deep along the bottom. But when you open up the drain, all of that, the heavier stratus, the heavier fluid, flows horizontally and then out the drain. A cold air drain is an upside down drain. If you look at it, if you turn it around, it looks like a wash basin. But we have a propeller inside, which is not the same as a wind machine. It doesn't make wind other than it blows, it dynamizes the air up, which pulls in the air along the ground. So it selectively extracts only the coldest air. It really recreates the same dynamics that a hillside does under those conditions. What we do is when we take on a project, we have to get information. What we do is we want to. We need to know the characteristics of the growing area, the block dimensions, where the blocks lay. We overlay that information over a Google map image, and that way we can see exactly with our contour lines. We'll build a 3D model and a 2D model, airflow models. One thing I do want to mention: we never charge for this analysis, but we don't sell the equipment without doing it, because it's an engineered product and it has to go in the right spot. If it's not sometimes intuitive what we're doing. It usually is, once you understand what we're trying to accomplish, you'll go, oh yeah, that makes a lot of sense. But it is site specific. It is, even though they're easy to move, they still have to go in that spot, and we modify airflows with dams, diversions, and other methods so that we can control this air fluxes coming in, the cold air fluxes coming in, and the cold air fluxes coming out. So we make up the models, we do all that, and so we do get the information out of you. You already probably have it in your head. You may not know that you have it, but you do. Even what you don't know tells us a lot about what's going on. There are 7 ways that cold air accumulates. And this is the one thing, when we start our analysis, we want to identify, why is this cold air accumulating in this method? Where is it coming from, and how can we block it out, and how deep is it, and how deep is the mass? There are 7 types. There's what's called there's basically 2 subcategories: dynamic airflows and static air masses. There's cold air rivers, cold air lakes, cold air flooding, plain slopes, lessening slopes, converging air currents, and flat area accumulation. This is what a cold air river looks like. That's a swale going through your vineyard. If you have damage that looks like a snake going through your vineyard, and it follows a gully or a swale or a creek, that's the cold air river. And one of the trademarks of a cold air river is that the damage pattern crosses your gradient lines. And we can tell if it crosses the gradient lines, we know it's a dynamic flow. Dynamic air masses need to be stopped before they can build up and cause damage. So in that case, we'll actually treat it from the upside down. We'll start from the top going down. The next ones are cold air lakes. This is probably the most common. It's what you hear about all the time. Basically, a cold air lake is just what it sounds like. It's an area where cold air flows into. If it was water flowing into it, you would build up a pond or a lake. You have things like road embankments, tree lines, heavy brush, just holes. All of those things can cause cold air lakes. And those are very, very simple to treat, because we get that from the bottom. Just like you drain a lake, you put a drain in the deep spot, or a swimming pool, you put a drain in and you get everything. You drain it from the deep spot. Cold air flooding. This one is kind of a tricky one, and this is probably the most dangerous, because there's almost an unlimited amount of cold air that can flood into your vineyard. What that is where you're planted on the upside of, I don't have a pointer, but when you're planted on the upside of the basin, you may have cold air coming in from both sides. Typically, that's like if you have a creek down at the bottom of your vineyard, and it goes up on both sides. You're not planted on this side, but you're planted on this side. But cold air is coming in from both areas of that basin, and it may be coming fast enough and not enough to actually cause an issue until it gets down into that low basin and starts to fill up, and then it floods back in. Just like if you had a house built on a river, and that river overflowed its banks. And then you would want to put a seawall in front, and then you would pump out anything coming over that seawall. You'd want to have a pump to remove that before it causes an issue. Plain slopes are also dynamic masses of air, and that's just what it sounds like. It's a straight, it could be a 4, 5, 6% slope going for miles, and as that cold air starts moving down, there's more cold air being added to it as it's going downhill, and so the mass of air you're getting more mass. The speed remains the same because it's the same. It's an equal slope, and so that cold air gets deeper and deeper, and at some point it will submerge the plant tissues, and from that point on down, you'll have frost damage. A lessening slope is basically where you might have a 10% slope coming off of a hillside, and then it goes to 5%. It's still going downhill, but the mass of air coming off of that slope is determined by the air shed area that's contributing to the flow. And the speed of that flow is determined by the angle of slope. So if you have the same amount of mass and you slow down the flow, the speed, you build up a deeper mass of air. And just like cars bumper to bumper coasting down a 10% slope, if it goes to 5%, they all pile on top of each other. And right there at the crux where it changes, you can have frost damage. So you can have damage right along the side of a mountain in that manner. And then as it opens up and goes downhill, that the cold air may have room to spread out, lessening the thermal boundary layer, and your frost is relieved. In all these cases, you could still have ice up at the top of the hill, because the ground up at the top of the hill loses just as much heat as the ground at the bottom of the hill, The difference is that there's no accumulation going on a hillside. That's why hillsides do not experience radiation frost. There's no accumulation going on. It all flows off. But you have ice there, but that's not frost. The next one is converging air currents. If anybody's a trout fisherman, you know how good that can be. Where you have two streamlines coming together, you get a pooling right there. And even though there's no obvious obstruction to the flow downhill, you have converging and chaotic currents, and you'll get a pooling, and right there is where you'll have frost damage. So we need to relieve that by removing that cold air. The next one is flat area accumulation, and that's just what it sounds like. It's flat. What happens there, flat areas are not typically frost prone as much as areas where you have cold air flowing into them, because they just don't have as much air. It takes time. That cold air just is built up right over, it's a static air mass, so it takes time to build up and submerge the plant tissue. So it usually takes longer, which makes it less intense. And one of the best ways to protect on a flat area is just raise your cordon height, and another foot, another half meter or less if you can. The high on flat areas you should have high cordons for frost protection. Now if you're going for other things, like flavor and different whatever your viticulturist recommends, you have to kind of balance that. Well, the first thing that we do is we do what we call an optimization. When we're doing an analysis, is we identify where these cold air flows are coming from and see if we can close them off. You may be in an area where you have a high mountain and there's a swale in that mountain or a gully that leads where all the cold air from the mountain gets funneled into that gully and then right into your vineyard. You may have a neighbor on this side of you and a neighbor on that side of you that has no issues with frost, because the cold air from that mountain is being funneled away from their vineyard into yours. In that case, what we want to do is we want to get up and build a wall. We want to close the door. And when we build a wall, a barrier, what happens then is that cold air comes just like a dam. It comes and water against a dam, it'll build up to the top of the dam. If there's enough volume, it'll build up to the top of the dam and then flow over the dam. When you see water that flows over a dam, there's a depth to that flow. So the lake behind the dam is actually deeper than the dam itself. In the case of air, a safe number is a 2-to-1 ratio. It can be up to 4-to-1 depending on the angle of approach to that dam. The lower the angle of approach, the greater the relationship will be between the air flowing over the thermal boundary, what we call the thermal boundary, flowing over that dam. So it could be up to 3-4 times the height of that dam. So if you see like a road embankment, for instance, and there's a gentle slope, a 1 or 2 or 3% slope going and hitting that road embankment, and that road embankment is 2 meters high, well, if you look at the frost line around that vineyard, you may see that frost line might be from the bottom there, might be 4 meters high or 6 meters high. And if you draw a straight line across it and down, you'll see what that relationship is, 1 or 2 or 3 times the height of that barrier. That's the potential based on how much cold air is coming in, and then at some point it has to flow out. So we want to identify where your cold air fluxes are coming in. We want to try to limit those.
Exhibitors and visitors. There's another pop-up tasting currently happening near Converging, site 40.
We want to limit cold air fluxes coming in, and we want to encourage cold air flows going out. You need to be very careful about. There's no really rule of thumb about removing shelter belts or obstructions down low. I hear a lot of times, everything below should be removed. That's not true. If you're in an area that you're subject to a flooding, because there's cold air coming in from the other side, you want that barrier there, because because it protects you from cold air coming in from the other side. Always before you remove any shelter belts, you should feel free to call us or send us an email with your location maybe marked off on a Google map. We will make you an airflow model. We do this every day. We do thousands of these a year. It's not an issue for us, and we will be able to, and you'll see it, and we'll be able to advise you whether or not you should remove that barrier or not. And we don't charge for that. That's something we just do. You should, it's a good resource for you. We're happy to do it. We do it all the time. For optimizing, there's also soil management. We will recommend how to manage your soil. Soil is a huge factor in whether or not you're going to have frost or not. You can, you see two vineyards that are identical. One has frost, one doesn't, and we start looking for other reasons. You start looking at maybe one of them might have sandy soil, the other one has clay soil. The sandy soil gets colder faster, chills more air. You have more massive cold air, and you have more submersion of plant tissues. Row direction. If you haven't already planted, we can advise you. You want to plant your rows to facilitate airflow out of the vineyard. Especially if you're on berms, those berms are little dams, and each one successively builds up a deeper and deeper thermal boundary layer, and at some point you're just not going to get any flow out of there. We want to look at row directions. Cover crops. If you're on a slope, cut your cover crop down. You have no choice. You have to get that cold air out of there. I know cover crops are beneficial, but you have to keep them low. You don't have to till it. We don't want you to till it for sure. Just mow it and let it grow back after the frost season is over. And there's also another issue with cover crop. When you talk about ice crystallization in the plants, plants don't get the cold. The temperature itself is a precursor to frost damage. It's not frost damage. You get into what's called a supercooled state, and that means that you have the potential to freeze. The molecules or the cells of the plant are cold enough to freeze, but they haven't frozen yet. It's the same as if you take a bottle of purified water and you put it in a freezer. You can get it down to -2, -4 degrees. If you take it out, it's still water. If you set it on a table and just leave it alone, it'll come back up to 0 and then it can't freeze. But if you shake it, you will cause ice crystallization. That whole bottle will freeze. Just the same as a beer when you pop a beer that's in a super cold state. So cover crops harbor what's called ice nucleating bacteria, and that is thought to be one of the predominant sources of nucleators for frost, for crystallizing plant cells. So by keeping the cover crop down, you keep those ice nucleating bacteria further away from the plants, less likelihood that they're going to incite the ice crystallization in the cells. So that's another benefit of keeping the cover crop down. That and airflow. Closing the front door is what we just talked about, where if you have an air mass, an airflow coming in, and usually a lot of times you can feel those. You know where they're at. You go, gee, when I go up and stand right up here, I get just freezing cold, and right there below it, where that goes, is where you have your damage. Removing obstructions to air flowing out of that's something that you want to take a look at. The cold air drains really mimic natural cold air drainage. They do the same thing forcibly that a hillside or Mother Nature would do if you had the right setup. And it makes you more naturally frost free. The more naturally frost free, what that does by stopping air coming in and helping air going out is it buys you time. It takes time for cold air because the mass of cold air is a constant. The BTUs, ground loses heat at a specific rate. And it doesn't matter whether it's a January night or a July night, because the radiation losses from the ground have nothing to do with the air temperature around it. They're not related. So, but the difference is a working number could be about 250,000 BTUs per hectare per hour of heat loss from ground. And it depends a lot on the type of ground you have, whether it's sand or clay or whatever. But that's a good working number. The difference is between a July night and a January night. January summertime, the nights are shorter. The ground has a lot more heat stored in it. So losing that 250,000 BTUs an hour is usually not much of an issue. In fact, in most times in July, the ground might not even ever get colder than the air, which means you're not even going to start to develop an inversion. Did I say it the wrong way? Okay, reverse, flip that. In January, yeah, wrong. I know. I'm still confused. In January or in July, during the wintertime, the nights are much longer, and the ground is much colder, so there isn't that much heat stored in it. An analogy to that would be, if you have, a bank, if you write a $1,000 check in a bank account that has $1,000 in it, you're empty. But if you write a $1,000 check in a bank account that has $1 million in it, you're not even going to notice it. So your wife might, but you won't. But so we want to limit. We want to extend that time to where the accumulation, covers the plant tissue, because really what we're waiting for the mothership to come save us, and that's the sun. When the sun hits the ground in the morning, you're done. It's over. Your frost night is over. You may have some residual cold air sitting in there. That's another benefit of cold air drainage, because it'll evacuate it very, very quickly. And the less time you are in that supercooled state, the less likely you are going to have ice crystallization in your cells. And that pretty much is a direct line correlation. If you have 100 hours a year that your plants spend in supercooled state, meaning they have the potential to freeze, and you reduce that to 50 hours a year, you're going to end up over a period of time with 50% less frost damage. That's just the way it works. So it's not really the actual temperature that causes the damage. It's the ice crystallization. If you're using current frost protections, cold air drainage is compatible with pretty much every method of frost protection, and it makes everything work better because even water. It makes it safer if you're using overtree water, and you can cut that down because we're getting rid of the coldest air. So the negative effects of, say, turning on an overtree vines, overtree sprinklers, that evaporative loss is lessened because there's less cold air that it has to overcome. Same thing with conventional wind machines. They get less effective as that cold air mass builds up because their effectiveness is based on the differential in temperature between the ground and where the blade is. So by keeping that temperature difference higher, they're more effective. You probably notice if anybody has any, they're very effective when you first turn them on. But as the night goes on, if they're in a pocket, as it fills up, they get less and less effective. You get less and less of a temperature increase. You can keep that going. The heaters, same thing. The way heaters work is you heat the air molecule, and it has thermal buoyancy. It rises until it becomes the same temperature as the air surrounding it, and then it stops. That's what you call your ceiling when you light up heaters. Does anybody use heaters or bogies out here? Do you guys have those? Because we don't need to go into it if you don't. It's not, heaters are very expensive to use, probably cheap to buy, but really expensive to use. Better if you don't even start it. Starting the site evaluation, you can speak to us. There's some little cards back there if anybody wants to grab one on the table or come over to our booth and we'll give you one. We'll contact you. We'll get the information we need out of you. It only hurts really just for a little while, but we'll pull it out. Fill out the evacuation, or you call us. Okay. That's pretty much I had for the prepared presentation. So I can open this up to questions. Does anybody have any questions?
There's a model similar to yours that's been in Australia previously. Yeah. Where there's known failures. Yes. Do you understand what failures have been caused by?
I know what you're talking about because in the late 90s, the developer of that was my partner was Dr. Guarga from the University of Uruguay. They marketed them, in different areas of the world, Australia and South Africa, and honestly, we didn't do that. That's one of the reasons we split up, because there was no mapping available. We can't sell a product until we can do the airflow models, and that data was not available here until about 2 years ago. It was only about 10 years ago we were able to do it for the United States, and a couple years after that into Canada. But because of political considerations, and it's all U.S. data, it's from U.S. satellites. And we have it everywhere. It's how they program. We use the same data that they used to program cruise missiles. They've been able to do that since the 60s, really. But they weren't giving it to us for commercial purposes. But it's only been less than 2 years that we've been able to do the Earth Explorer and get the data from the satellites off of that so that we could, and that's why we never marketed outside of the United States and Canada. When they first started doing it, I know that Rafael and his protege, Pedro, which I don't think either one of them are doing it anymore. We're actually going on site and doing a physical visit, which is possible, but it's very time-consuming and very costly. We never did. So, and I've heard, in fact, I had somebody today that said they picked some up on the used market, but, you can't do that. They're site-specific. It's an engineered product. If you just take one of them, think of it as a machine and throw it out there, it's a global effect. If you're not, it's like putting a pump out. And I think one of the comments that he made to me was that it doesn't work on a hill. No, it doesn't work on a hill. It's a pump. It's like if you put a pump on an island in the middle of a lake, it's not going to drain that lake. It's got to be in the spot that you're going to facilitate that drainage, and you have to control inflows going out. If you're draining it into a spot where you're just going to get more air in there without blocking that out, well, then you're going to accomplish nothing. So it's very, the volume of air that you're trying to remove, the size of the basin has to be modified. All of that has to be done. It has to be an engineered, and then they work like nothing else works. They work, we have over 3,000 machines out throughout the world. Every single one of them has an analysis. Every one. And, I'm sorry. Yes? Yeah, without that, but I can't tell you why without doing analysis, I can't tell you why theirs failed. But we have picked up several. Since we started going out, yeah, we've heard of several that have been like that. But they're not our product, and it's not, so. Yes, did you?
Yeah, if the machine pumps the cold air straight up, what's preventing it? You're in a gully, what's stopping it? Right back there.
Stopping it from coming back?
Coming down, yeah.
Coming down the gully along the ground?
Like if you're in the river situation and you're pumping it up and out.
Does it come back down? No. There's two processes that goes on. One is we don't need to say one is called is selective extraction of the stratified fluid. The other is called Ascendant Mixing. And what happens when you have a column of fluid going through a static mass of fluid moving? It's a venturi. It has the moving mass has less pressure. So as the jet stream is going up through the warmer stratuses, it starts bringing in the warmer air. And in our design, and I don't know if it's true of their design, but in our design, every approximately three diameters of the machine. So if you're using our 1550, which is approximately 8 feet diameter, every 24 feet, that volume of air that's in that column doubles. And because it's bringing in air from outside. And it's getting warmer. And there's assimilation taking place. There's time for heat transfer between the molecules coming in and the molecules that we've taken off the ground to transfer heat. So those molecules, those cold, heavy, dense molecules along the ground are getting larger and lighter and less dense. That also provides much of the lift. That's why it gets up to almost 91 meters above the ground with very low power. But once it's up to about 90 meters, it's actually, depending on the calculation that you use and some variables, it can be between 73 and 91 meters is how high that jet stream goes. Once it gets up there, those molecules might be just a tiny bit cooler than the ones around them, so they will drop back down, but they can only drop back down to where they're neutral, to where they're the same. A warmer molecule cannot go below a colder one. It's not possible. It's impossible. It's physically impossible. So they'll only drop down a little bit, and then they drain horizontally. It is called a cold air drain. That is the correct terminology. Whereas a conventional wind machine is a wind mixer. It mixes the warm with the cold. That's also correct terminology. But the air that we're draining off is gone forever. It can never come back. but it's being generated all night long. Now, as far as, there's another point, another half to that, or I don't know if you didn't ask this, but I don't know if you were getting to this or not, but when we drain cold air from a basin, we don't pull more cold air in, because it doesn't do that. It works just like if you have a drain in a swimming pool, or you have a lake, and you have a river flowing into that lake. The flow of the river going into that lake has nothing to do with the depth of that lake. If that lake, it doesn't make it flow faster or slower or anything. It doesn't affect it at all, because what's feeding that river and what's feeding the cold air coming in is the heat loss from the air sink above it. That's going to go on whether or not you drain that accumulation going in. And so there's no, it doesn't suck air. You won't feel air being sucked into the machine except right around the machine. The local effect. And it doesn't affect it like that. That accumulation doesn't have anything to do with it. Does that answer your question? Okay, anything else? Okay, dismissed. No, I'm just kidding. If anybody wants to start the evaluation, like I said, we don't charge for that. You can get out of the way, and you'll be able to get an exact cost and start planning for it. If you want to do, for next year, the year after, or 5 years from now. If you're going to plant a new vineyard or a new area, let us do the mapping for you, because if you can avoid planting in a cold air and accumulation area, you're miles ahead. Now, sometimes you can't. Sometimes you have a limited amount of space, or you're already planted there, and it makes sense to plant and just fix it. But you can recognize that you're going to have a colder area. When we do what we call a preventative area, we have one. We just basically make the assumption that everywhere that's going to accumulate cold air is going to have a frost issue. That may or may not be true, because different varieties have different criteria for when they're going to have frost. Even though the temperature, if you plant a Cabernet Sauvignon in one spot and you plant lemons in that same spot, you got the same temperature, but the vineyard, is going to have a frost issue, and the lemons, of course, won't or might not. So it's not about what you plant, and also you don't need to take direct temperatures. Radiation frost is not a weather event. I know I said that before. It has to do with what's called unobstructed radiation losses. The longer you have no wind and no clouds, the more likely you're going to have this deeper accumulation. It takes time in every spot you have, from the time you have no wind and no clouds. It's good. We're done with it. It may take 2 hours, for instance, for enough cold air to flow into that pocket, that frost pocket that you have, to actually cause a problem, to submerge the plant tissue. So if a wind comes up every hour, it blows it out, and you may lose 1 degree. So maybe it's 0 here, and now it's -1. Wind comes up and it's 0 and 0. Then an hour later, and it's not a frost night. But the next night, same temperature at sundown, same ground temperature, same humidity, identical, but no wind and no clouds for 6 hours. Still 0 here. But down here, now it's -4 or -5. That's a frost event. So it's not a weather event, it's a microclimate event. It has to do with unobstructed radiation losses. If you continually drain that air out of there and it doesn't accumulate, you simulate a non-frost night. You won't know the difference between that night. If you looked on a data logger, it'll look like it was a cloudy night, that you had no inversion. It'll look like a cloudier, or probably not a windy night, because wind, when you look at data loggers, you can see the wind like this, but a cloudy night goes like that. So basically, that's one of the biggest comments we get is that, we didn't have frost damage here for the first time in 10 years, but I never got cold down there. Yeah, that's what it's supposed to do, and it doesn't. Really, what we say about cold air drains is that when they run, nothing happens. You won't see a thing, because when you have frost, something happens. You get a temperature separation. When the sun goes down, it's the same temperature in your frost pocket as it is up on the hills. And on a frost night, you get that temperature drop difference. It separates. It gets colder down in that frost pocket. And with a cold air drain, it doesn't. It'll stay the same all night. or close to the sun. That's what we're trying to. That's what we're trying to do. Which is why we want to see how high up the damage goes. We want to know where your damage pattern is. That's really important to us because you may have a really deep valley, but the frost line only goes up halfway. We don't, and maybe it's 4 degrees colder from the top to the bottom, but it's only 2 degrees colder from your frost line to the bottom. Well, it may only take one machine to make that frost pocket equal the microclimate, equal the same climate as where you don't have frost, but to get it to equal the top, it might take 5 machines because it becomes exponentially more difficult as you have a higher area. That's also one of the same reasons that your frost lines are very consistent. It's like the water line of a lake. If you have a lake and you raise the depth of that lake by 1 meter over its normal capacity, that's a huge event because the surface of that lake now becomes 5, 10, 100 times larger than the natural lake bed. So that's why it's very consistent. You see these water lines, it goes that high, that's it. That's as high as it goes. It would take a biblical event to make it go up much higher than that. Not that it can't happen, it can. You can have those biblical events, and that's farming, Okay. So, okay, that's... any other questions? There's a lot of information on our website, a lot more than I'm giving you here. It's shurfarms.com.
The 4 p.m. supply presentation, one titled Panel Discussion, Doing Things Differently, Practical Success in the Vineyard, will be commencing in 15 minutes, free on the Wine Tech Seminar stage.
So anyway, and there's also a book that is published. You can get it. It's available on Amazon, called Cold Air Accumulation and a Grower's Guide to Frost Protection. And it goes through analysis. It goes through how you can evaluate different ways to see if your region where you're going to plant is suitable for what you're growing, doing executive studies. And there's also a microclimate study that we do. Let me see if I've got it here. Real quick. And I think we have a brochure on it. But it's this right here. And it's a microclimate map, and what we do with this, basically, this is available if we need to do it. We would do an analysis, but we only will do it if it's really necessary, where we just compare areas, where you're planting, we compare accumulation areas, we identify those, and then we compare the temperature differentials in those accumulation areas as opposed to the control where you don't have accumulation. And so you would know where to focus your efforts on. If you have an area that's 4 degrees colder than the control and an area that's 1 degree colder than the control, well then you want to focus. Start there first. Start with your coldest spots first, and then take it up from there. So that's a tool that's available for you also. Any other questions, comments? Okay, thank you.